Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics 3, RLT College of Science, Akola. Dear student, in previous lecture we have seen some types of singularity. Okay, so in this lecture we will see theorems on a singularity. So what is the statement of the theorem? The statement of the theorem is if f has an isolated singularity at z equal to a, then the point z equal to a is a removable singularity if and only if limit z tends to a, z minus a into f of z equal to 0. So this is the statement of the theorem. Okay, so what is given? So let us suppose that the given point z equal to a be an isolated singularity of the function f and limit z tends to a, z minus f of z equal to 0. Then we have to show that z equal to a is a removable singularity. So we will show this theorem in two parts. So first part we will see, given that the point z equal to a is an isolated singularity, so therefore by using the definition of isolated singularity, there exists r greater than 0 such that f of z is analytic in open circle AR minus singleton A. So let us we define to prove this theorem function g on open circle 0 AR tends to C. Okay, sorry, open circle AR tends to C, and which is defined as g of z equal to z minus a into f of z, where z is not equal to 0. When z equal to a, so this will becomes 0. So let us we consider equation number 1. So here g of z is analytic, then we can say that that is a differentiable function, and that differentiable function is also a continuous function. So therefore g of z is a continuous in a open disk whose center A radius r except the possible point at z equal to a. So now we will check the for the continuity at z equal to a. Consider limit z tends to a, g of z equal to limit z tends to a, z minus a f of z. So this will become 0 at z equal to a. Okay, and g of a equal to 0. Okay, so which implies g of a equal to 0. The equation number, this is equation number 2 and this is equation number 3. Okay, now from equation number 2 and 3 we can say that g of z limit z tends to a, g of z equal to g of a, because this is RHS is 0. So from this equation number 2 and 3 we can say that both values are equal. Okay, so therefore we can say that g of z is a continuous at z equal to a. So if the function is continuous at z equal to a, then we can say that that is also continuous on open disk whose center A radius r. Okay, so actually we have to show that g of z is analytic in open disk whose center A radius r. So for that we will use the Morera's theorem to prove this theorem, that is g of z is analytic. Okay, so that is we will prove that the for every triangular path T in open circle whose center A radius r, that means we have to show the integral T g of z dz equal to 0. So clearly there are four different cases. First is point A lies inside T, second point A is vertex of T, third is point A lies on the side of T, and fourth is point A lies inside the T. So these are the three possible different cases. Now we will check the first case. Let point Z equal to A lies inside the T. T is a triangular path. So let us we consider this is the open disk whose center A radius r, and this is the triangle T. This is the triangle T. Okay, and let us we consider A is any point which is lies outside of this triangle. Okay, so therefore by using the definition of g of z, g of z is analytic in a open disk except the possible at a point A. Okay, so this is g of z is analytic in this open circle, but at this point g of z will not be analytic. So when the point A lies inside T, so therefore by Cauchy's theorem, we can say that integral T g of z dz equal to 0, where T is a closed curve. Okay. Now we will check second condition. Case number 2. Let point Z equal to A is one of the vertex of the triangle T. Okay. So let us consider this is the open disc whose center A radius R center A radius R. Let us we take the triangle T, draw the triangle T. This is the triangle T, whose vertex are A, B, C. Okay, so let us we consider Z equal to A be the any vertex of the triangle T. Okay, so therefore let the triangle T is a triangle ABCA. ABCA. Choose the point X and Y on the side of AB. So let us we take X is the midpoint of AB and Y is the midpoint of the AC. AB and AC of the triangle T and join XY. Then the triangular path T is divided into two parts. One is triangular path, triangle AXYA, and second another is a polygonal path, that is XB, or we can say that XBCYX. Okay, and also let us we consider L be the length of the triangle XYA. So therefore this triangle can be written as integral T g of z dz. Okay, the triangle will be the, that is AXYA. The path of the triangle is AXYA g of z dz, plus second integral g of z dz polygonal path, that is XBCYX. But here g of z is a analytic if the point z is inside the uh, circle. Okay, but here z is lies outside of the polygonal path. So therefore by using the Cauchy's theorem, integral g of z dz polygonal path xbcy equal to 0. Okay, so this term will become 0. So therefore integral t g of z dz integral triangle axy g of z dz, equation number 5. Now taking mod on both sides, we will get integral over t g of z dz less than equal to integral over triangle path axy g of z dz. But we know that the g of z is a analytic function, and which is a differentiable function, also continuous function on a open circle whose center radius ar. Okay, so therefore g of z is continuous at a point z equal to a in a open circle. So therefore by using the definition of the continuous function at a point z equal to a, for every epsilon greater than 0, for epsilon is epsilon by L, there exists delta greater than 0, such that mod z minus a less than delta, which implies mod g of z minus g of a less than epsilon. So which implies g of z minus g of a less than epsilon by L. So by choosing this epsilon. Okay, but we know that g of a is 0 by using the definition of the g of z from equation number 1. So this can be written as mod g of z less than epsilon by L. Okay, so this is equation number 5. Now we will use this equation number 5 in equation number 4. Then equation number 4 will be written as equation number 4, that is equation number 4, integral t g of z dz less than equal to integral of triangular path axy g of z into mod g of z, and putting the value of g of z, that is epsilon by L mod dz. Okay, so this can be written as epsilon by L is a constant term, so take outside of the triangle. Then in triangle only mod dz, and we know that the value of this mod dz, that is L, length of the path, that is L. So this L and this L will get cancelled, so only a remaining will, that is epsilon. Okay, but here epsilon is a arbitrary constant, so let us we choose epsilon is a 0. So therefore integral t mod g of z dz equal to 0. Okay, so here we have proved second case. Now in third case we will see, let the point z equal to a on lies on the side of t, on the side of t. Okay, so let pqr be the vertex of the triangle t, and the point a lies on the side pq, and then we will join a with opposite vertex r. Then the original triangle T is divided into two triangles. Let us reconsider T1 triangle and T2 triangle. Okay. Then T1 such that point A is one of the vertex of the T1 T2. Okay, as shown in figure. Okay. So this is the open disc whose triangle is T. PQR, and A is the midpoint of PQ. Then we will join, this is AR, and this triangle is divided into two parts, T1 and T2, where A is the midpoint of the P and Q. Okay, so in this way we can show the figure. So this can be written as triangle T divided into two parts, that is integral T g of z dz equal to integral T1 g of z plus integral T2 g of z dz. So by using case number 2, the integral T1 g of z dz is 0 and second integral T2 g of z dz is 0. So therefore this will become integral T g of z dz equal to 0. Okay. Now final step, final case is case number 4. Let the point z equal to a lies inside the triangle T. So this is we consider that this is the triangle open disc whose center a radius r, and this is the triangle, that is triangle is BCD. So let us consider BCD are the vertex of the T, and T is a triangular path. Triangular path is BCDB. BCDB. Okay, and join all the vertex of the triangle T with A. Then the triangle T is divided into three triangles, say T1, T2, T3 as shown in figure. So let us we consider BCD is one of the triangle in this open disc, and A is a middle part or midpoint of the these three vertex, and then we will join this all the points. Okay, so this will form a triangular path, that is BCDA of this triangle. So by joining all the points to A, then this triangle is divided into three parts, T1, T2 and T3. Okay. So therefore integral T g of z dz can be written as integral T1 g of z plus integral T2 g of z plus integral T3 g of z dz. Okay. So here if you observe the point A, which is the vertex of the triangular path T1, T2, T3. Okay. So this is the A is the any vertex of the this triangular path T1, T2, T3. Okay. So this A is the vertex of T1, T2 as well as T3. So therefore by using case number 2, the integral T1 g of z dz equal to 0, integral T2 g of z dz equal to 0, and integral T3 g of z dz equal to 0. So this all will become 0. So putting these values in this integral, then the integral T g of z dz equal to 0. Okay. So from the case number 1, 2, 3 and 4, we prove that integral T g of z dz equal to 0 for any triangular path T in an open circle whose center A, radius R. So therefore by using Morera's theorem, then we can say that G of Z is a analytic on a open circle whose center A, radius R. Okay. So therefore now by using the definition of G of Z, equation number 1, G of Z has a 0 at Z equal to A. That is G of A equal to 0. So therefore there exists analytic function h of z on an open circle whose center A, radius R, and which is given as G of z equal to z minus a h of z, where h of A is not equal to 0. So therefore by using the equation number 1 by the definition of G of z, this can be written as G of z instead of h of z we will put f of z, where z is not equal to 0. Okay. So f of z equal to h of z, f of z equal to h of z for every z belongs to open circle AR minus singleton A, and h of z is analytic on a open circle center radius R. Okay, so if you put here g of z, z minus h of z, so this will become f of z into h of z. So therefore z equal to A is the removable singularity of the function f of z. Now we will prove the converse part of this theorem. Suppose that f of z has a removable singularity at z equal to a. Then we have to show that limit z tends to a, z minus a, f of z equal to 0. Okay. So suppose that f of z has a removable singularity at z equal to a. So therefore by using the definition of the removable singularity, there exists a function g of z in an open circle whose center a, radius r, such that this can be defined as f of z equal to g of z for every z belongs to open circle whose center a r minus singleton a. Okay. So let us consider to prove this converse part of this theorem. Limit z tends to a, z minus a, f of z. So limit z tends to a, z minus a, f of z, put z equal to a, so you will get 0. Okay. So here this will become 0, and hence we can say that the converse part of this theorem is proved. Okay. So here in this way we can prove the singularity theorem. Okay. So in next lecture we will see another theorem on a singularity.